Look, another FBD KD here. We have a crate shown that's being lowered by two cranes. It says again, knowing the tension in each cable. Draw the FBD KD. So let's go ahead and do that here. Let's draw on the free body side and on the kinetic side. So we've got tension A, tension B. Got the center of gravity sitting there, and again, from that is a 400-pound force. Over here on the kinetic side, I've got mass times acceleration in the y direction. There'll be no acceleration in the x direction, and I would also have the possibility of I bar alpha. So again, I would be needing to calculate the moment of inertia. And if we again look at our unknowns and unknowns, right, an unknown alpha, an unknown AY. So I've got two unknowns, and I'm going to have two equations upon which to solve those for. Most likely some of the forces in the Y, and then I'm also going to spin a moment. Give you a moment just to read this. We've got object, ABC, an L-shaped member. Couple of different weights on there. It says AB has a weight of 2 pounds. BC has a weight of 4 pounds. We're told that when theta equals 0, we have a known angular velocity. So omega is equal to 10 radians per second. Determine the components of the reaction. So again, we're just going to draw the FBD KD here. So let's just go ahead and draw that member twice here. I've got two weights to this. I've got a half foot here. I've got half foot from a dimension. I've got 1 foot and 1 foot. I've got 4 pounds. I've got 2 pounds. Up here, again, at theta equals 0, I've got a CY and a CX. Again, I can just treat these, again, these two things as separate. So again, over here, I've got now two centers of mass. And both are going to be, again, relative to a fixed point, which is up there at C. So we've got fixed axis rotation. So at the midpoint of CB, we have mass of CB times ACB in the x direction. We'll go ahead and put our coordinates on. All right, this is going to be in the tangential direction, again, relative to point C. We also have MCB times ACB in the y direction. And again, that's going to be the normal direction. And we also have I bar of CB times alpha. And again, there's only one angular acceleration for the total body. So down here at the midpoint of AB, I'm going to draw a dashed line. And so we've got also mass AB times acceleration AB in the tangential direction. We also have mass AB times acceleration AB in the normal direction. And also we have I bar of AB times alpha. And so we've got some kinematics to help us out here. We can highlight triangle in there, which would be 2.5 inch, and this would be R. And so if we solve for R, you end up with 2.0616 feet. And so we end up with some, let's see, we've got some relationships here that the acceleration of AB in the normal direction would be equal to omega squared r, which would be 10 squared times 2.0616. We also have the acceleration of CB in the y direction, which is going to be omega squared times 1. Right, its lever arm of 1 foot, 10 squared times 1. And two more here. We know that the acceleration of AB in the tangential direction is going to be equal to alpha times r. So that's going to be alpha times 2.0616. And then acceleration CB in the y direction is going to be equal to alpha times 1. And I'll also identify an angle here. I'm going to call that angle beta. So the tangent of beta is 0.5 over 2, giving me that beta is about 14 degrees. And again, that's going to show up right there as 14 degrees. And again, also right there.